While NDBs are a dying technology, our next nav aid is still very much alive and much more common in the National Airspace System. This type of nav aid is called a very high frequency omnidirectional range, also known as a VOR. The typical VOR is usually white and resembles a big bowling pin. However, other types of VORs exist that look much different. Since VORs operate within the frequency band of 108 to 117.95 MHz, they fall into the space wave spectrum. This does allow for relatively interference-free navigation. However, reception is limited to line of sight, which prevents a pilot from receiving a signal when at low altitudes or in mountainous terrain. VORs are oriented to magnetic north and transmit radial information outward in every direction, similar to spokes on a bicycle. Technically speaking, there are an infinite number of radials being broadcast out, but for simplicity, it is said that only 360 radials are used. In the airplane, the VOR indicator consists of three vital parts: the course deflection indicator, or CDI, the to-from indicator, and the omni-bearing selector, or OBS. The OBS knob is used to choose the course, or radial, that you'd like to reference. The to-from flag will tell you whether the radial selected will take you toward the VOR or away from it. And finally, the CDI tells you how far off you are from the center of the course in degrees. Now you may be asking yourself, Self, what's the difference between a radial and a course? Well, they are really the same thing. However, when flying, radials are directed away from the station, whereas courses are directed toward the station. So, when you fly away from a station, you want to follow a radial. When you fly toward a station, you want to follow a course. The reason for the distinction is because the VOR indicator, in its old-school fashion, does not know what the aircraft's heading is. Let's say you are directly south of the VOR flying northbound. You could dial in either the 180-degree radial from or the 360-degree course to into the OBS, and both will tell you that you are on course. However, if you start drifting to the west, you'd get two different indications on your instrument. The instance where you have 360 degrees to selected will indicate that you are left of center. However, if you had 180 degrees from selected, the instrument will actually indicate that you are right of center. This type of situation is called reverse sensing. If you were not aware that you had mistakenly entered the reciprocal radial into the instrument, the more you tried to correct toward the center, the further off course you would actually get. Modern-day avionics, like the Garmin G1000, use a horizontal situation indicator, or HSI, instead of the old standalone instruments. HSIs merge your heading and navigation into one instrument, and because of that, does not succumb to reverse sensing, at least with VORs. However, a pilot navigating with an HSI should still always dial in the appropriate radial or course, because if by chance there was a failure with the instrument and it no longer synced with your heading, you would not want to suddenly encounter reverse sensing. Since a VOR's radials emit out like spokes on a bicycle, the closer the pilot flies to the VOR, the more sensitive the instrument gets. Let's again say that we are south of the VOR on the 180 radial, flying northbound. We set the OBS to 360 degrees, and we get a to indication. The closer we get to the station, the more sensitive the needle gets, but the indication will continue to show to. As you pass over the top of the VOR, you enter a zone called the cone of confusion. The cone of confusion is the area above the VOR where the airplane does not get a clear signal. The to-from indicator will go to the off position because the receiver can't quite tell where you are. As you fly away from the VOR, the receiver gets the signal again and the flag flips to a from indication. Now you can track the 360-degree radial from the VOR and continue flying northbound, tracking the radial away from the station. If at any time you want to figure out where you are in relation to a VOR, all you need to do is find what radial you are on. That means that on your indicator, you need a centered CDI needle and a from flag. Simply keep rotating the OBS knob until the CDI centers. If by chance it's centered with a to flag, you are on the reciprocal radial. You need to rotate the OBS 180 degrees left or right. It will center once again, this time with a from flag. So, by using one VOR, you would know where you are in relation to that VOR. However, you don't know at what point you are along that specific radial. For that, you'd need either distance measuring equipment, or DME, or a second VOR. The DME will tell you how far from the VOR you are, pinpointing your location. Two VORs can accomplish the same thing through a process called triangulation. To triangulate your position, pick two VORs that are near you and tune in their respective frequencies. Now, simply center both needles with from flags to find the radials. Use a sectional chart to draw the radials out. The two radials should intersect, indicating your current location. Before any flight that you intend on using your VOR receiver, you should make sure it works. FAA regulations require you to check your VOR equipment every 30 days for IFR operations. It's not required for VFR operations, but it's a good idea to test it anyway. When pilots perform a VOR check, a record of it is kept in the airplane. This log contains the date of the check, the location of the check, any bearing errors encountered during the check, and finally, the pilot's signature. Keep in mind that before you actually rely on a particular VOR for navigation, you need to make sure you have the correct VOR tuned in. This is accomplished by identifying the VOR. Just like in NDB, VORs transmit out three-letter identifications in Morse code. After a pilot tunes in a VOR, they need to listen to that VOR's audio transmission and make sure the Morse code matches what it's supposed to be. Pilots do not, however, need to know Morse code. All they have to do is match the audio with the dots and dashes printed on the sectional chart for that station. Unlike an NDB, pilots do not need to continually monitor the audio of a VOR. Once they have identified the station, they can turn the audio off. If the VOR was inoperative, the to from flag would show off. As part of another convenience of today's advanced avionics packages, systems like the G1000 can identify a VOR for you. Once you enter the frequency into your navigational radio, the G1000 displays the VOR's identification next to it. If that ID matches what's on the sectional, you have the right station tuned in. You do not need to listen to the Morse code, unless you want to, of course. Just like with NDBs, there are different classes of VOR, each with their own service volumes. VORs have a power output necessary to provide coverage within their assigned operational service volume. There are three service volumes that a VOR can have: terminal, low, and high. A terminal VOR is one usually located on an airport and is a lower powered VOR. It has a range of 25 nautical miles and reaches an altitude of 12,000 feet AGL. A low VOR is more powerful and has a range of 40 nautical miles and reaches an altitude of 18,000 feet AGL. And finally, there's the high VOR. This VOR is used to build the high-altitude airways that exist from 18,000 feet and above. This VOR is higher powered and has many layers to it. The first is from the surface up to 14,500 feet AGL and has a range of 40 nautical miles. The next layer is from 14,500 feet to 18,000 feet and a range of 100 miles. Above that is a layer from 18,000 feet to 45,000 feet and a range of 130 miles. And finally, the top layer goes from 45,000 feet to 60,000 feet and has a range of 100 miles. The rounded shape at the bottom of these service volumes is depicting the line of sight characteristics of the VOR. The way to tell what kind of service volume a VOR has is to check the airport facility directory and look next to the VOR name for the symbol in parentheses. VORs are shown on a sectional chart with this symbol, surrounded by a compass rose. This helps pilots visualize and draw out radials for their flight planning. Just like with NDBs, in the vicinity of a VOR is a box of information relating to that station. It includes the same pertinent information as an NDB would have. Sometimes VORs have distance measuring equipment, or DME, as well, and will be shown by this symbol. The third and final way a VOR is shown on the chart is when it is co-located with the military TACAN. This VOR is then called a VORTAC. A TACAN is just the military equivalent to a VOR system. You may also notice certain radials being drawn on the sectional connecting different VORs together. These are known as Victor Airways and serve as predefined low-altitude routes that pilots can use to navigate along. So now that we've covered all that, let's go over how a VOR actually works. Remember that a radio wave looks like a sine curve. If you have ever taken a trigonometry class, you might remember that the sine wave has some key points: 0 degrees, 90 degrees, 180 degrees, 270 degrees, and it starts over again at 360 degrees. The VOR uses this concept to operate. The VOR emits two signals, a reference phase and a variable phase. The reference phase emits outwards in all directions simultaneously. The variable phase emits outward in a rotating fashion similar to a lighthouse. This would be a fast lighthouse rotating around 30 times a second. Older VORs were mechanically rotated. Now they are scanned electronically to achieve the same result with no moving parts. As the variable phase signal rotates around the VOR, the signal will become phase shifted from the reference phase. The two signals are detected by the aircraft's VOR receiver and then compared to determine the phase angle between them. So at 90 degrees, the two waves are phase shifted 90 degrees apart. The phase angle is equal to the direction from the station to the airplane. So this airplane is on the 090 degree radial from the VOR. The same idea is true at the 180 radial and the 270 degree radial. The two signals are phase shifted and the airplane receivers can detect this difference. As previously mentioned, one of the ways pilots get distance information is through something called Distance Measuring Equipment, or DME. This system operates on frequencies in the UHF spectrum between 962 MHz and 1213 MHz. Similar to other systems, DME emits a Morse code ID every 30 seconds to indicate that it is operating correctly. The range of DME is 199 nautical miles, but it only serves the closest 100 aircraft. They are also subject to line-of-sight restrictions, just like a VOR. To obtain distance from a station, your aircraft's DME receiver first transmits a signal to the station. The station then replies back. The aircraft's receiver then measures the time it took to complete the trip and converts that into distance. Because of that, DME gives the pilot something called a slant range distance. This means that the distance shown is actually going to be the exact distance to the DME station, not the distance across the ground. So an airplane at 3,000 feet might get a DME distance of 0.6 nautical miles, when in fact the plane is 0.5 nautical miles away from the DME. The effect worsens at higher altitudes. In fact, if you fly over a VOR at 6,000 feet, even though you were right on top of it, the DME will tell you that you are 1 nautical mile away from it.